In this lecture, we're going to introduce what integer programming is. To start, we're going to review some things about linear programs. Here we have the general form of a linear program written. This is the general form. And there's not a whole lot we need to know about linear programs, aside from the general form and taking the dual. If we have a particular linear program, usually we're going to have a linear objective function. Let's say the sum of ci times xi. And we can expand our constraint matrix to have particular terms. This might be a more familiar form if you're used to actually working with linear programs. We'll always have the constraint that xi is going to be greater than or equal to 0. This is going to be a linear program. Frequently in this class, we're going to have to take the duals of linear programs. Taking the dual of a linear program is relatively straightforward, and we can look it up elsewhere. Here I'm just going to write it down so that we know exactly what it is. We'll use the same constraint matrix. And now we have a different variable yj. This is the dual LP. We'll see the dual arise a lot. What's important about linear programs, aside from just knowing what they are and taking the dual, is understanding the geometry of them. Here we'll do a little bit of a tour of what the geometry of a linear program should be. We have a particular linear program here in just two variables, x1 and x2, with two constraints, one here, and the constraint that all the x's are greater than or equal to 0. We can draw these two constraints on the plane we have. First we'll draw the constraint that x1 is greater than or equal to 2.5. There's going to be a horizontal line at 2.5, and all points towards 0 are going to be feasible. Our other constraint, we'll say, draw it in green, x2 is less than or equal to 3. We can draw this, and again, all points that are headed towards 0 are going to be feasible. Finally, we have to draw our objective function. And the way we think about our objective function is we draw a line that has a constant value for our objective function. So, for example, we can draw the line between 2 and 2 here. And this is part of our objective function where x1 plus x2 is equal to some constant. In this case, that constant is equal to 2. What we'd like to do is, in a linear program, slide this objective function up as high as we can, because this is a maximization problem, until we almost get outside of the feasible region. In this case, this means that we're going to draw our line up here intersecting the blue and the green lines, where we have x1 plus x2 equal to 5.5. And this point at the very top is going to be our optimal solution. And at our optimal solution, we can see that x1 is equal to 2.5 and x2 is equal to 3. This is the main idea. We're going to take a linear program, and to think about it geometrically, we're going to draw the different constraints, and then we're going to draw a constant function for our objective and slide our objective up as high as it will go until we almost get outside of the feasible region. You can see that our optimal point right here is at the very edge of the feasible region. This is how we think about linear programs geometrically. So why are we talking about linear programs? Integer programs are intimately related to linear programs. There's a few different varieties of integer programs. The first is not exactly the most general, but the one we'll be working with most often. Here we're going to be maximizing some objective function, usually a linear function, subject to some constraints, x is less than or equal to b. And now, instead of having a constraint that x is less than or equal to 0, we're going to force all of our x's to be integers. That is, all of this x vector is in a vector of natural numbers. This is an integer program. We're also going to be working with mixed integer programs. Mixed integer programs are the most general form that we're going to be working with, but it's only occasionally that we're going to have to use the entire power. We're going to abbreviate these by MIPS. Whenever we use solving software, this solving software will work with this most general class of mixed integer programs. In a mixed integer program, we again have an objective function But we break it up into two pieces. There's going to be two sets of variables, x and y, and each one of these is going to be associated with a different part of our objective function. We're going to have a constraint matrix, again AX, but we're also going to have a constraint matrix for these y variables. This will be less than or equal to some vector b. The x variables in this case are going to be any real numbers. We'll just say that x is going to be greater than or equal to 0. Y, on the other hand, is going to be a vector of natural numbers. And we can see why this is a mixed integer program. We have both real valued numbers, these x's, and integers, these y's. The final class of program we're going to look at is binary integer programs. Binary integer programs are an important special class of integer programs. In this case, we're again going to have an objective function, maximize, say, f of x, subject to some set of constraints, x is less than or equal to b. But now, instead of having x being the vector of natural numbers, x is going to take on two particular values, 0 and 1. And it'll be a vector of 0, 1s. The most important point to understand integer programs is again to understand the geometry. Here we have written a integer program, and on the other side we have our previous linear program diagram. We've written our constraints, and the constraints are going to be the same. That is, x1 is less than or equal to 2.5 is already visualized, and x2 is less than or equal to 3 is also already visualized here. We've also drawn our previous objective function, x1 plus x2, and we have it intersecting these two constraints. The difference between a linear program and an integer program is this additional set of constraints. x1 plus x2 is in the natural numbers. This effectively induces a lattice. The only feasible points for x1 and x2 aren't any continuum of values, but these discrete lattice points. Here I'm drawing some of the lattice points. What this integer program does is define the set of feasible lattice points. So these are the feasible lattice points. Instead of having a solution that's going to just satisfy our linear constraints, we need to have a solution that's going to satisfy our linear constraints and also lie on this lattice. So this point over here is no longer feasible because it doesn't lie on our lattice. x1 is equal to 2.5. Instead, what we need to do is take our objective function and effectively slide it down until we hit our first lattice point. Our first lattice point is where x1 is going to be equal to 2 and x2 is going to be equal to 3. This effectively reduces our linear or objective function, but now it's feasible for these integer points instead of just any points at all. In future lectures, we're going to continue to look at integer programs from this sort of geometric perspective.